Okay, well, I'm Jordi Baylina. I'm the technical lead at Polygon zkEVM, as was explaining. As you all know, we launched the Polygon zkEVM in 1 month and a half before. For many of you that don't know, zkEVM mainly is a layer 2 solution that it works exactly the same way that Ethereum. That means that you just connect your your MetaMask to the chain, and you can do exactly the same thing that you would do in Ethereum, like creating a smart contract, deploying a smart contract, using exactly the same tooling, the same thing. So that's the same that Ethereum. The only difference is that the price should be much cheaper, and the number of transactions that support the EVM is much smaller. So this is for the last, let me just see. Okay, so this is a little bit what I'm going to be talking. At the beginning, I'm going to explain a little bit what's the current status of the EVM, and then I'm going to talk a little bit about the near future, and in the last minute, I'm going to explain a little bit the long future, at least how I visualize the space of the rollups space, the layer 2 rollups space. So let's start. Well, right now, the current status of the network is, well, so far so good. It's working really hard. It's working really good. We had no stops at all. It's working, I would say, perfect, much better than we expected. Just for you to know, for example, the only things, a lot of applications have been deploying their application, testing the deployment, or even checking and producing. Most of the applications, I mean, they have no issues. They just take the smart contract, they deploy, and they tell you, okay, that's working, and that's fine. And in general, we don't have to talk with them. That's a nice thing of the EVM. The only thing that the only small thing that we are working is something in the timestamps. Timestamps right now, we are having some issues, especially in the accuracy of the timestamp, because we are doing batches to bigs, and next week we are going to fix that thing, and we expect that some of the DeFi applications, especially the ones that require oracles, that they will be up and running. But this small thing probably has been the biggest issue that we had so far. Okay, so everything is working okay, and the question is what's going next? Actually, we have been like two years working really hard to put this in production, and once we're in production, we realize that we just started. I mean, that everything just starts now, because now is when we really want to scale. Okay, the first things that we want to, I would say, finish is there is a couple of precompiled smart contracts that are not implemented yet. These are SHA-256 and pairings. These are the only two things that are not implemented to be a type 2 rollup. So once we implement that, we will be a type 2. Right now, we are working really hard on these smart contracts, and in the next upgrade, this should be fixed. Another thing is, well, it's a small detail, is just remove the zk counters, and more on that later. Okay. Well, to remove these zk counters, actually, we are changing a little bit the structure of the proof. The proof that we have right now is we say it as a monolithic proof. It's a big proof. It's a proof that you need half terabyte machine to compute it. It has all the pieces in a single proof. It's many state machines. It's like many subprocessors, but all of them create a single proof. Okay, so what we want to do that is using recursion to have a proof that's a composite proof. It's a proof that's composite of many sub-proofs. So that means that this will allow us to have a smaller proofs. And what's better is that so in this monolithic proof, all resources are the same. For example, ketchucks, we have about 2,500 ketchucks in the proof. If we are using all of them, that's okay. But if we are using just 50 ketchucks, we are still paying the full proof itself. So it's not very efficient on that. With this system, with this kind of proof, it allows you to have different sizes. For example, a proof for 50 ketchucks, another for 100, another for 200, another for 400, and so on. And then you choose, depending on the proof, that you choose which, depending what you want to prove, you choose this different proof on here. Okay, this will allow us to do more optimal things. Okay. Another thing that you can do with this is using recursion. Instead of having, for example, one binary state machine, you can have 3 different binary state machines and then aggregate them together. So you can keep the size of the subproof small. So all these, well, these are the advantages of you doing this, is we don't waste cells in the stack somehow. We don't need to count the resources. One of the things that we have right now is that we need to know so you need to prove that you cannot prove something. So, and how you do that? Well, what actually is, for example, when before doing a ketchup, we keep an accounting of how ketchup remains not used. And if we don't have enough ketchups, then we just finish the proof, but we finish in the right way, and we said that there is not enough ketchups, so maybe this is an operation transaction or whatever it is, okay? But this forces us to keep an accountability of all the resources itself. If we have this kind of proof, because they are more extensible, you can work with the limits, and this allows you to scale as much more. So all these counters, which is a little bit the difference between the layer 1 and the layer 2s, we can read out of these counters. Okay? And also the other interesting thing is because these subproofs are smaller by itself, this would allow to run these proofs, for example, in GPU or in FPGAs. Right now, the problem is that these proofs, they run in a CPU with this big machine, and this does, 500 gigabytes doesn't fit in a GPU. But 10 proofs of 64 gigabytes, they fit in the GPU. So we believe that with this, we will reduce a lot the cost and accelerate a lot and the proof generation with this new version. Okay? To do that, for generating this proof for the zkEVM, we built a language that we call PIL. It's polynomial identity language. And this has been very useful for writing all the arithmetization on the zkEVM. Currently, we are working with a new version, with an extension of PIL. We call it PIL2. And well, here I'm going to do a little bit of summary of these new things that will allow us to build in PIL2. Okay. Well, the first thing is that we will support in PIL2 these BATCOPs, these variable degree composite proofs inside the PIL. The PIL right now, you put all the identities, all the constraints. It's just one line after the other. And with this new PIL2, it's going to be a more constructive language. So you will be able to build all these constraints like in a programmable way. Okay. This goes. Okay, so you can have variables, you can have loops, whiles, for each functions, and everything related to that. And this will allow us to build much more complex circuits in a more programmable way. Okay. Functions, for example, to do some components, you can have some functions, libraries, and itself. Okay. Here we are at one thing that's very typical in the Starks, that's the boundary constraints. Right now we don't have boundary constraints. Actually, we do it manually with a single things, but here we allow us to build boundary constraints on the system. The other thing that we are doing now is that we allow to we define these stages. Right now, we have like one single stage, and we have a high level language. For example, for lookups or for permutation checks. The idea now is that we will be able to define polynomials at different stages, and we will define also challenges at different stages. So this will allow us to build new constructions that, for example, the permutation check is not going to be something that's specific from the language. You will build a permutation check with their own language, or a lookup, or any other fancy or difficult constructions that you can have there. So somehow, PIL is going to be a lower level language, but PIL is going to be written in PIL. So PIL somehow, okay? So we simplify the language somehow, but we make it more complex. We can do more complex things, okay? Another thing is right now, all the fixed columns right now are just constant columns, okay? Here we distinguish with repetitive fixed columns and generic columns, okay? And another thing is that all the constant generations will be included also in PIL. So for the auditing, you will not have to go to a special program that you use to generate the language. You have everything here in PIL, okay? Another thing is right now, in PIL, you can access only to the current row and to the next row. Here we add in the language to access to different parts of the rows. Of course, this will require openings in different places, but this allows you to be more, to create more readable, or if you want to work with a star that works with different rows at the same time, you have everything in the language. Okay. For range checks, well, actually, a range check is going to be a function for itself, so we put everything here on that. Okay. And another important thing is, okay, from the language, when you are building a circuit, of course, you need to build mainly two things. One is this identity system, the set of constraints, but you need to build also the witness generation. For building the witness generation, you need a lot of information that talks from PIL. Okay, so we add here a way to communicate from PIL to the witness generation for helpers there, so they can go together from one side to the other. Okay, some built-in functions. Lookups at the end are going to be functions. Permutation checks are going to be functions. So proof permutation checks. Oh yeah, because we have these multiple different variable degrees to prove, we have a full system to communicate between the different state machines. Okay, matching and so on. Okay. Okay, this is mainly, this is an important because I think that this is going to be a good way to generate proving systems with polynomial-based systems. Okay. One of the topics that we are working very much right now is data compression. Right now, as you know, one of the biggest limitations is data availability. So we work very much with data compression. And data compression, just to go a little bit fast here, is well, when you have data, if you see how the data is compressed, in general, you see the data and it's a command with parameters, okay? For example, one command can be put just raw data, don't compress anything, or rewrite something, reuse some part of the data, or for example, if you have a value that have a lot of zeros, you can have some standard techniques for compression. But this is not the most important thing. The most important thing is, well, there is one thing that, for example, is easy to compress. Well, it's relatively easy to compress. One thing is, for example, removing the signatures. And the idea here is substitute a set of signatures that will be in a blob with proof that you hold these signatures, okay? And the cool thing here is that you don't even need to prove that on chain. You can put this proof with the same blob and then recursively check these signatures in there. So we can remove all the signatures in there, so there's a huge win in the compression. The other part that's important is, for example, the addresses or sometimes the hashes. it's a lot of, this data is very difficult to compress because an Ethereum address is kind of a random, so it's difficult to compress. So here the technique that we're using is that we keep a kind of a state of all the transactions that has been made in the last blocks, and then you can access to this address by reference. So the first time that you use an address, you will have to put the full address, but then you will have then to access an address, you will have a single reference. Okay. Well, I'm going to jump a little bit this. Okay. Well, just to go fast, we'll have like two kind of rollups, one for processing data, the other for processing transactions, and it's going to be two pipelined rollups itself. Okay. Here is in compression, and these numbers from the last weeks, these are very optimistic. These are pessimistic numbers. Actually, we are going to do it a little bit better than that, but we expect that data compression will give us a 5x in cost. Okay, that when you add that to the EIP 4844, that's 10x. On top of that, we expect that the cost, the data availability cost, once the EIP 4844 is going to be like 50x cheaper in the rollup. So expect, here the thing is that expect that in less than in half a year, 1 year at most, the costs for the L2s is going to be much cheaper than what we have right now. That we are, currently we are something like 10%, like 90% cheaper than L1 already. Okay? Other points of work is, other points to work is the node performance. Of course, the scalability is very much about that. Processing transactions, sequencing the transactions, synchronizing the node, this, having better database, better cache. It's a full work here in the node itself. Just one detail here is for account abstraction. The cool thing of being zkEVM is that we get that for free. I mean, because you just need an EVM to run the ERC 4337, so the system, without designing itself, we already have, we will have account abstraction fully compatible with 4337. We just need to deploy the 4337 smart contract and then allow bundles to send the transactions there. Decentralized sequencer, this is probably the hardest topic, but it's important to decentralize the sequencer. In Polygon, we are working in that direction. Security, of course, is a non-stop thing. Keeping investing in security is a thing. Continuity auditing, all the new versions, it's important to work in the security. Training wheels, well, we should remove very easy, very soon the forced transactions. This is going to be maybe in 1-2 weeks. We will enable that. But then we want to be in the trailing wheels too, as soon as possible. This requires removing the security conceal and extending the upgradability to 30 days. Okay, so this is a little bit the roadmap that we have for these years. The idea is to deploy all these new versions with this data compression by the end of the year. Well, we'll see the 4844 when it comes, but as always, it's not a commitment, but this is the plan that we have right now on the table. And just to finish, oh, that's it. Oh yeah, here it is. Just to finish, here is a little bit more in the long run. This is how I see the L2 space. So the idea is to have, of course, you have a lot of L2s, chains that can be different chains. They should have maybe, well, they have a common liquidity pool. Maybe this liquidity pool will connect with other rollups and with other liquidity pools in other chains. Okay, and the idea is that all these chains, they can have a proof aggregation. So this can be a set of actors that can generate the proof in a coordinated manner in a consensus layer to generate a single proof. And at the end, in Ethereum, you have a single proof where you have the proof of all the chains itself. Okay, Of course, these chains, they can be with centralized sequencer. With the centralized sequencer, there's probably going to be some staking hub where they can stake in the different consensus that goes in here. So these are the three pieces, but the idea is that you can have a full ecosystem of chains with composability between chains, because there is going to be one single proof for all the ecosystem. You can generate a proof maybe every 30 seconds, and this will be like a clock. And then the composability you can call from one rollup to the other and the other to the one. This is the nice thing of zk's, that you can have these small timings between inter-rollup communication, because you don't need to wait for these fraud proofs for this space. So this is a little bit the future that we are expecting, and this is in the long run, and this is a little bit how we plan in Polygon to move forward. Okay, so this is very much my talk, and thank you very much.